is Dr. C. Vidyarani, Assistant Professor, Department of Chemistry, V.V. Venniyaperumal College, Varuman, Virudhunagar. Today we are going to discuss about band theory of semiconductors with its types. Let us see the introduction of band theory. So, band theory, the word implies there are three types of bands: conduction band, valence band and forbidden band. How these bands are formed? Actually, all the matters are made by atoms. So, if we take any solid structure, it is having n number of atoms, and this n number of atoms will occupy different energy levels, and these atomic different energy levels will overlap with each other to form a strong a strong bond. That band is termed as energy band, or we can say based on that energy band formation we are explaining the band theory of semiconductors, and the gap or distance between the bands are called as the band gap. Different types of bands are there. One is conduction band, valence band and forbidden band. Let us see what is meant by valence band. So actually valence band, it is the lower energy level and highly occupied energy levels, and it is having the maximum number of electrons in its. So this valence band acts as a donor and it donates the electron to the conduction band. It is highly occupied by the electrons. So this is the smaller and highest occupied energy level, and electron will jump from this valence band to the conduction band, and it lead to form the external energy there. And what is conduction band? So conduction band is the highest energy level band, but it is either partially filled or sometimes it may be completely empty, and it acts as an acceptor. That means it is always ready to accept electrons donated from the valence band. So we are saying that as a conduction band, and due to flow of electrons or charges in this conduction is taking place there, and it lead to the conduction properties for the semiconductors. So this is the basic role played by the conduction band. Actually in valence band it is inert, whereas in conduction band the movement of electron lead to the conductions. Let us see on the third type of band, that is forbidden band. So forbidden band is nothing but this also a type of energy band between the two conduction bands and the valence band. These two bands are divided by a distance, and that distance is termed as a forbidden band or forbidden gap. That means in this band no electrons are we cannot identify any electron in the gap between the conduction band and the valence band. So based on the difference in the distance between the conduction band and energy valence band, or you can say that is a forbidden gap, it discusses the types of materials. That's what we are saying as conducting material, insulators, semiconductors. So the classification of these materials are based on the forbidden band, or you can say that is the forbidden gap. This is the energy gap diagram for different materials. So three different band variation we have shown here. A is for insulator, B for semiconductor, C for the conductors. From the picture it is clear the distance between, the variation of distance between conduction band and valence band is shown here. First we take the conductors. For example, metals, all the metals act as the conductors. Here the distance between valence band and conduction band, it is very minimum. The forbidden band or the energy gap is very less. So in some cases overlapping of these two bands, that means valence band and conduction band, they may mix with each other. So the electrons in the valence band can easily transfer to the conduction band, and it lead to electrical conductivity there. Second, we see that in between we are having the semiconductor. So semiconductor, if we compare it with the insulator and conductors, it's the forbidden gap. The distance is somewhat lesser than insulator, and it is greater than conductors. If we see the distance gap here, the conduction band, it is when you are comparing with conductor it is very less, whereas here it is somewhat larger when compared to conductor. So it needs some external support to transfer electron from valence band to conduction band. So semiconductor show the conductivity. It shows the flow of electron or conduction, or it shows the electrical property when it is induced by some external support. Whereas in insulator, you see here the band gap is very high. The forbidden gap between the valence band and the conduction band, the distance is maximum here. So the transfer of electron from valence band to conduction band, it is very difficult for the electron jump. So no conduction is happened for insulators. Whereas in semiconductor, by applying some external force, by using some external support, the transfer of electron can take place there. So let us discuss on holes and electrons. They plays the important roles in semiconductors. We know holes are positively charged carriers. That means the deficient of electron is denoted by that positive charge. That positive charged carriers are termed as holes, because these holes and electrons both are act as the charge carrier in electrical conductivity. So these positively charged holes, they also plays the important role for conduction in semiconductors. Whereas electrons, they are negatively charged particles. When you are comparing these holes and this electron, both are magnetically same but opposite in their polarity. Let us see about the mobility of electrons and the hole, which is having the maximum mobility. If we comparatively do this, these electrons are having the maximum mobility when compared to the positively charged holes. Why? Means for the positively charged holes, due to some strong atomic force by the nucleus, it retards the free movement of the holes. So that the electrons are showing the high mobility when compared to the positively charged holes. Then let us discuss on the types of semiconductors. Actually, we can classify the semiconductors into two types. One is intrinsic semiconductors, another one is extrinsic semiconductors. So intrinsic semiconductors are otherwise termed as pure semiconductors. We can say otherwise as a pure. Why there? Means here we are not mixing any impurities there. So you can say these intrinsic semiconductors as pure semiconductors, and the elements which are acting as intrinsic semiconductors are germanium and silicon. Whereas for external semiconductors, they are again classified into two types. One is N-type, another is P-type. This N-type semiconductors, how these N-type semiconductors are formed means due to mixing of some impurities called pentavalent impurities, and P-type semiconductors, they are formed by mixing of trivalent impurity. So you can say these external semiconductors are formed by some mixing of impurities. So you are saying that impurities as dopant. So you are saying other was this external semiconductor as extrinsic semiconductor as impurity semiconductor, whereas intrinsic semiconductor as the purest semiconductor. Example, if you see for N-type semiconductor, so pentavalent, so its valence shell should have the 5 electrons. The 5 electrons, we know actually the covalent bond is formed by sharing of 4 electrons in its valence shell. Here 5 electrons are there, so one of the excess electron, it lead to the conduction here. The examples for N-type semiconductor pentavalent dopants are phosphorus, arsenic and antimony. We know that. And the P-type semiconductors, they are formed by doping with the trivalent. So trivalent, it is deficient in one of the electron in its valence shell. So it is always ready to accept the electron from the donors. So example for this trivalent dopants are gallium, boron, indium, aluminium. So these are the examples for these types. Let us discuss it one by one. What is the intrinsic semiconductors? I already told you, it is the purest form of semiconductor. So no any mixing, external mixing or dopant is used there. Just by making the thermal energy is enough to break the bond between the atoms. That covalent bond can be easily broken by rising the temperature. At 0 Kelvin, it is, you see the picture here, at 0 Kelvin, it is inactive, inert. All the electrons are equally shared by the atoms, so the bond is not breaked here. So electron, the free movement of electron is not observed at 0 Kelvin. If we rise the temperature, the bond between the atoms is break to release the electron, and these electrons will show the free movement, and this free movement of electron lead to the conduction of the material. You see the energy band diagram for intrinsic semiconductor. So A is the intrinsic semiconductor at a temperature T is equal to 0 Kelvin, and B is the energy band gap, or the distance between the conduction band and valence band is shown here at a temperature greater than 0. If we comparatively see here in A picture, we cannot identify any electrons in the conduction band there. Why means there is no breaking of that band, no movement of electrons we are observing at 0 Kelvin. So all the electrons are present in the valence band. So at if you are rising the temperature greater than 0, what happen means the bond between the atoms is breaked. Especially you can take a silicon atom or germanium. The bond between the adjacent atom is breaked there and it releases the electron, and this electron is now free to move in its structure. So the movement of electron is shown in picture B. If we see the conduction band, some electrons are replaced here from the valence band. So the conduction band is acting as an acceptor and the valence band is acting as a donor here, and it leads to conduction in intrinsic semiconductor. Next, let's see about the extrinsic semiconductor. So I already told you extrinsic semiconductor is a impure form of semiconductor. Why means because we are mixing some impurities there. Some of the element is additionally mixing there to show the electrical conductivity. So that mixing impurities are called by the name dopant. So dopant, and the process of mixing this atom is called as doping. So doping is one of the process of mixing impurity with the atom which are inactive, which are inert for the conduction. So this is again classified into N-type and P-type semiconductor. So I already gave the example for this N-type. So all these elements is having 5 electrons in its valence shell, and the excess one of the electron is free to move to give the conduction. Let's see the picture here. So this is the image for N-type. So center we are having the surrounded by silicon, and this bond between the silicon and the lead, it may break and it lead to formation of 4 electrons is shared by silicon and the lead, and excess one of the electron is shown here, and this movement of electron it lead to conduction for this N-type. Whereas in P-type the electron doping or mixant here is boron, and this boron is made to bond with the silicon. So it is a trivalent, so it is having a hole. The hole is represented here. That hole, that positive charge carrier, the hole is responsible for transport or conduction of current here. So this charge carriers, both these charge carriers, negative electrons and the positive holes, both are charge carriers, and these two are responsible for conduction of semiconductors in N-type and P-type. So these are the examples. Apart from borons, we can use aluminium, indium or gallium in their places, and it lead to the formation of a hole or positive charge carriers in its structure, and it acts as, it is ready to accept the electron, and it acts as a acceptor here. Thank you.